In the last lesson, I mentioned briefly that carbohydrates exist primarily in their cyclic hemiacetal forms. So now I want to explore in a little more detail what this means. Okay, so I want to take you back to a reaction of aldehydes and ketones, and I want you to recall that aldehydes or ketones can react with one equivalent of alcohol under either acidic or basic conditions to form a hemiacetal. Okay, so in this case, I have methanol reacting with isobutyraldehyde, and these two starting materials are in equilibrium with, in this case, it's an acyclic hemiacetal, in which the carbon indicated with the arrow contains both an ether oxygen and an OH group. So since sugars in the open chain form have an OH group on each carbon, they can carry out this reaction intramolecularly to give the cyclic hemiacetal form. Okay, so on the right is the drawing of glucose in the form that we most typically see it drawn in the open chain form. What I have done on the left here is I have taken the same molecule and drawn it in a suggestive conformation. So what happens in this case is that the OH group on C5 is actually the one that is in proximity to the aldehyde at carbon 1. So I have this molecule drawn so that the OH substituents occupy equatorial positions. That is actually what makes glucose glucose. The stereochemistry is such that all of those non-hydrogen atoms on carbons 2, 3, 4, and 5 can occupy equatorial positions once we form a six-membered ring. So you see how it is primed to do the ring closure and form the six-membered ring. I have a couple arrows drawn just showing the formation of the oxygen-carbon bond and the cleavage of one of the carbon-oxygen bonds of the aldehyde. This is not meant to be an exhaustive mechanism. It's just a guide to show you where the electrons are coming from and where they're going. So furthermore, as the arrows show, the equilibrium favors the cyclic form. So the ratio of cyclic to acyclic is actually greater than 99:1. So when the cyclic hemiacetal contains a six-membered ring, as it does in the structure of glucose that I showed on the previous slide, we call the structure a pyranose. And the name is derived from pyran, which is a six-membered ring containing an oxygen and two double bonds drawn on the right side of your screen. However, it is also possible for open chain sugars to form a five-membered ring cyclic hemiacetal. And you should have been in this course long enough by now to realize that 5- and 6-membered rings are the two most favorable ring sizes. Okay, so let's consider fructose, which is a ketose. So in order to be a ketose, the carbonyl group cannot be on carbon 1. If it were, it would be an aldehyde, and it would therefore be an aldose. So being a ketose, the carbonyl is on carbon 2 instead of on carbon 1. So what that means is that if we take the OH on carbon 5 and use it to attack carbon 2, we end up getting a 5-membered ring instead of a 6-membered ring, of course, with the oxygen being one member of the ring. So you can see drawn here as the product, we have a hemiacetal. The hemiacetal carbon is now carbon 2 instead of carbon 1. There is a CH2OH coming off of carbon 2, as well as a CH2OH coming off of carbon 5. So this form is called a furanose because the 5-membered ring oxygen heterocycle with an oxygen and two double bonds is called a furan. So glucose tends to exist exclusively in the pyranose form, six-membered ring, because we saw just how wonderful that six-membered ring is with trying to get its substituents equatorial. But fructose actually is a mixture of furanose and pyranose forms as the two cyclic hemiacetal forms, and it has a significant amount of furanose at equilibrium. Okay, so that's a little bit about the cyclic hemiacetals, but what I've also alluded to is that I can put all of the non-hydrogen atoms in glucose into an equatorial position when we form the cyclic hemiacetal. And the reason for that is the specific configuration at each of the carbons that are stereocenters in glucose. So in order to understand any more about what's going on with sugars, we have to actually start looking a little more in depth and systematically at their stereochemistry. And that's where we will pick up in the next lesson.